Hi everyone, and welcome back to the basics of rheology. This is episode 2, and today we are diving into a really exciting question. Now that we understand what viscoelasticity is, how do we actually measure it? Spoiler alert, a viscometer won't cut it. To measure viscoelasticity, we need a more advanced and powerful tool, the rheometer. So how does a rheometer actually work? It applies a force or motion to a material and measures how the material responds. The raw signals it collects include torque, the twisting force, angular displacement, how far it twists, and angular velocity, how fast it twists. But these are just raw signals. To get meaningful rheological properties, we need to translate them. Well, here's the good news. You don't have to do the math yourself. Our Rheometer software uses built-in constants that are specific to the geometry you are using. These constants automatically convert the raw signals into shear stress from torque, shear rate from angular velocity, and strain from angular displacement. So now we know how we apply force or deformation and how we measure the response. But what kind of deformation can we apply? Rheometers can perform 3 types of deformation: rotational, steady shear like a steering, transient, applying a constant stress or strain over time, and oscillatory, back and forth motion to probe both solid-like and liquid-like behavior. And here's the key point. To measure viscoelasticity, we mostly use transient and oscillatory tests, something viscometers simply can't do. And with a steady shear, we can scout viscosity over a wide range of shear rates. Now you might say, but viscometers can at least measure viscosity. And yeah, but rheometers take it a step further. They can measure viscosity across a much wider range of shear rates and offer significantly better temperature control, both of which are essential for getting accurate, reliable, and reproducible results. Now let me show you just how sensitive our rheometers are. Imagine I'm holding a 1 meter long, slim stick. Now I place a single grain of salt, just around 0.05 milligrams on the other end. That tiny grain creates a torque of about 0.5 micronewton-meters. And guess what? Our rheometers can detect even smaller torques than that. This level of sensitivity is what allows us to study even the most delicate material behaviors, from soft gels to biological tissues. Now, you might be wondering, how do we apply that torque to the material? That's where the geometry comes in. Just as an engine requires the correct fuel to operate efficiently, a rheometer relies on the appropriate geometry to ensure accurate and reproducible measurements. The geometry is the shape of the tool that holds and deforms the sample, and it directly affects how we interpret the raw signals. Depending on the material and the design task, we choose different geometries. Cone and plate, great for low viscosity fluids like oil. It gives a uniform shear rate and it is very precise. Parallel plate, good for soft solids or samples with particles. It is easy to load and trim. And quet, cup and bob or vane in cup, ideal for low to medium viscosity fluids. it helps reduce evaporation. And it doesn't stop there. We also have different sizes, surface finishes, and materials for geometries, depending on the test. Size affects sensitivity and how much sample you need. Surface finish, smooth or rough, helps prevent slip or improve contact. And the geometry material, that depends on chemical compatibility and temperature range. All of these factors help ensure accurate and reliable measurements. At TA Instruments, we offer two main categories of rheometers, each with its own native mode of operation. Stress-controlled rheometers, their native mode is to apply a known torque and measure the resulting angular displacement or velocity. They use a combined motor transducer design, where a single unit both applies the torque and measures the response. Our Discovery Hybrid Rheometers and Discovery Core Rheometer fall into this category. They are versatile, user-friendly, and ideal for a wide range of applications. Strain-controlled rheometers, their native mode is to apply a known angular displacement or velocity and measure the resulting torque. It features a separate motor and transducer configuration, which allows for ultra-precise control and measurement by isolating the actuation from the sensing. That's the specialty of the Aries U2, a high-performance instrument designed for researchers who need the most accurate rheological data. Each type has its strengths, and the best choice depends on your application, testing needs, and material itself. So to characterize complex fluids, including measuring their viscoelasticity, we need three key things: sensitive instruments, smart geometries, and the right type of deformation. Each part of the rheometer and rheometry, from the torque transducer to the geometry to the test mode, plays a role in helping us understand how materials behave. In the next episode, we'll explore how we actually run these rheometry tests.